Have you ever stopped to think about where the internet actually lives? I don't mean your Wi-Fi router, but the actual, physical home of our entire digital universe. Well, today, we're going to take a journey through the past, the present, and the absolutely wild future of the computing infrastructure that powers our world. So, let's just start with that big question. When you stream a movie or you jump on a video call, where is that data really coming from? Where is it going? The answer is right here. It lives inside these enormous, almost city-sized digital factories that we call data centers. These are the real physical engine rooms of the internet. And that brings us to the first part of our story, the age of centralization. You know, for the past couple of decades, the game has been pretty simple. Build bigger, more powerful, and more efficient data centers. Now, take a look at this map. What's crazy is that this shows the global footprint of just one major cloud provider. Every single one of those dots is a massive cluster of servers. This isn't just a network. It's basically a global nervous system. The scale is almost impossible to wrap your head around. And yeah, the money behind it reflects that scale. To build this thing, top investors have poured in over $53 billion. That's the kind of cash it takes to build the literal foundation of our entire digital economy. But it's not just about the machines. This industry employs 1.2 million professionals all over the world. We're talking the engineers, the technicians, the security experts who build and maintain this whole operation. And the innovation, it's just relentless. The industry has filed over 76,000 patents, constantly pushing the envelope for more efficiency, more power, and of course, better ways to cool down all those servers. This chart really shows you the global race that's going on. China is leading in the sheer number of patent filings, with the US right behind. It's a full-on competition to define the next generation of data center tech. Okay, but here's the twist. This whole centralized model, it's starting to hit a wall. Why? Because of the sheer explosion of data coming from billions of devices, our phones, our cars, all the sensors out there. Sending every little piece of data to a central cloud and back is just becoming too slow. And this brings us to Act 2, the age of distribution. To solve that data bottleneck, we're seeing this massive shift. We're pushing computing power away from the central cloud and out to the edge of the network, way closer to where all that data is actually being created. So you might be thinking, well, hold on, why can't we just build faster connections to the cloud, right? Why is this move to the edge so important all of a sudden? Well, it really comes down to the speed of light, or what engineers call latency. The cloud is centralized and incredibly powerful, sure, but it's physically far away, which means higher latency. The edge, though, is decentralized and close by, which means it can respond almost instantly. And for things like competitive online gaming, or a self-driving car, or remote surgery, that split-second difference is absolutely everything. This whole idea leads to a new model called the Edge Cloud Continuum. So try to think of it less as cloud versus edge and more like a spectrum. It's a layered system that uses the right tool for the right job, blending the pure power of the cloud with the lightning speed of the edge. And this continuum has layers. So you start with a massive centralized cloud. Then you move out to what's called the near edge, maybe some regional data centers. Then the far edge, which could be a tiny server in a 5G tower. Then you get to on-premise, like on a factory floor. And you go all the way out to on-device computing, happening right inside your phone or your... So why does all this matter? Well, because this new architecture is what's going to make all those futuristic things we hear about actually possible. We're talking smart cities that react to traffic in real time, factories that can predict failures before they happen, and remote healthcare that can bring a specialist to a patient anywhere in the world. Okay, so we've gone from a centralized cloud to a distributed edge. But what's beyond that? This brings us to our third and final act, the next great leap into the age of quantum. So what happens when we run into a problem that even our huge cloud and our super fast edge just can't handle? I mean, problems in drug discovery or creating new materials, things that are just fundamentally beyond what our current computers can do. This is where quantum computing enters the picture. And the engineering behind it is it's mind-blowing. As IBM says here, their processors have to be kept in an environment that is literally colder than deep space. That's the kind of extreme condition you need to harness the bizarre laws of quantum mechanics. And progress is happening really fast. Just look at the increase in qubits, which are the basic building blocks of a quantum computer. See, a normal computer bit is either a 1 or a 0. A qubit can be both at the same time. This means the processing power explodes exponentially as you add more. This isn't science fiction anymore. This is real technology that's scaling up year after year. Now, here's a really crucial point. Quantum computers are not going to replace the laptop or phone you're watching this on. They are highly specialized machines designed to solve a completely different class of problems, the ones we currently think of as, well, unsolvable. So let's pull all of this together. We've really journeyed through 3 distinct but connected ages of computing. Here's the roadmap. Today, we're living in the era of the centralized data center. By 2026, that distributed edge cloud continuum is expected to be the new standard. And then, by 2029, the goal is to have the first truly stable, fault-tolerant quantum computer online, ready to start tackling those unsolvable problems. That's an incredible pace of change for the next decade. This whole journey from a centralized cloud to a distributed edge, and now toward a quantum future, is really a story about bringing computing power closer and closer to our problems. So the final question is this. As this incredible digital engine gets smarter, faster, and physically closer to us than ever before, what are we going to build with it?